All right. Good morning, and it's week 9, so just a little bit of time left, I guess. All right. Okay, so we will continue covering different topics here, and so today we will look at the EM algorithm, or at least one specific case of the EM algorithm, I should say, or a specific application. So the EM algorithm is the expectation maximization algorithm, and we can use this in situations where we have both missing data and unknown parameters. Okay, when you have only one of these things, it's not too hard to estimate what you need to estimate. So you can guess the missing data, or you can generate your missing data. You can estimate unknown parameters if you only have one of these things are unknown. But if both of them are unknown, then it's a little bit trickier. Okay, so here's the first scenario where a value is missing, but the parameters are known. Okay, you know the parameters. So let's say we're told the values 1, 2, and x is unknown are drawn from a known distribution, and that known distribution is a normal distribution with mean 1 and standard deviation 1. Okay, so what is our best guess for the missing value x? Well, we'll look at the normal distribution and we say, well, its peak is at the mean of 1, and so our best guess for x is going to be the mean of the distribution, and we'll just say 1. Okay. Here's another scenario where the values are known, but the parameters are unknown. So let's say we're given the values 1, 2, and 0, and I tell you that they're drawn from a distribution, except this distribution, the mean is unknown. So it's a normal distribution with an unknown mean, standard deviation 1, and what is your best guess for the mean mu? And so this time the mean of the distribution is unknown, but you're going to use maximum likelihood estimation, and you would say the mean of our sample, okay, is going to be the best guess for the mean of the distribution. So we'll do 0 plus 1 plus 2, and this gives us a mean of 1, and so we'll plug in 1 as our best guess for mu. Okay, so that's great. But what about this scenario? Let's say we have some data that have a missing value. So we have 1 and 2 and unknown value x. And I tell you they're drawn from a distribution. And this distribution is a normal distribution, but the mean of this normal distribution is unknown. So what do? What is your best guess for the missing value of x and the missing parameter mu? And so this is a little bit trickier. And so we can take a kind of an iterative approach. Okay, so first we just kind of start off with an arbitrary guess for mu. So I'm going to just guess 0, and if I plug in 0 for mu, then I will say, okay, well, if mu is 0, then my best guess for x is going to be 0. All right, and if that is the case, then my data is going to be 1, 2, 0, and in that case, then my best guess, then I iterate back and forth, and I'm going to estimate what's my best guess for mu. Okay, in this case, 1, 2, 0, my best guess for mu is going to be 1. Okay, and now this is going to bother me. Okay, well, I don't know. Our best guess for mu is 1, and then so now if I have to plug in what is my best guess for x, okay, I'll use mu, okay, and then now my data is updated to 1, 2, 1, and if that's the case, then my maximum likelihood estimate for mu is going to be 1.333, the average of 1, 2, 1. Okay, this is not any better. And then, and we keep iterating back and forth between updating my missing value x and updating my best guess for mu. And eventually we will converge to my best guess for x is 1.5 and my best guess for mu is 1.5. Okay, that's what we end up getting. And that's kind of the EM algorithm in its like most simple form. Is you have these two steps. One is you have an E step, an estimation step, and then you have an M step, a maximizing step. Okay, so in our case, the E step, which is estimating your missing values of x, okay, estimating your missing values, and then your M step is updating your unknown parameter to kind of be your maximum likelihood estimate. Okay, so so that's kind of how it goes, and you iterate back and forth between these two steps of updating your missing values and then updating your parameter guesses. And so we'll apply this to a situation where we have Gaussian mixtures, okay? A mixture of normal distributions or a mixture of Gaussian distributions. And so the data that we have are going to have been generated by several different Gaussian distributions, except we don't know which distribution that a data point came from. Okay, so our missing data is which distribution a point belongs to, because we'll have basically the value of the point. And if we're dealing with multivariate, we might have like an x and y coordinate of our point, or an x1, x2 coordinate. And then we also have it came from distribution A, or it came from distribution B, or distribution C. Okay, and so the parameters of these Gaussian distributions, however, are also unknown to us. We don't know the mean and variance of the Gaussian distributions. And so we're going to use this EM algorithm to iteratively figure out the unknown parameters of our Gaussian distribution, as well as kind of the unknown cluster assignments. So as an example, I'm going to just do a simple example where I have 3 multivariate normal distributions in 2 dimensions, and we're going to have cluster 1, cluster 2, and cluster 3. Okay, cluster 1 will represent 50% of our data, cluster 2 will be 30% of our data, and cluster 3 will be 20% of our data. Okay, and so this vector alpha represents the mixture proportions. Okay, so this is kind of like I don't know, the recipe, okay, of our data. 50% come from cluster 1, 30 from cluster 2, and 20% from cluster 3. All right, and obviously alpha can be basically any, vector of any length for how, however many mixtures you have, how many distributions you're mixing together, and then the sum of alpha has to be 1. So our first component will be a multivariate normal distribution centered at 0, 0, and its sigma matrix is going to be 9, 0, 0, 9. So it's going to have kind of a lot of variance, but the variance in the x1 direction is 9, the variance in the x2 direction is 9, but they are independent, so it's going to be just kind of like a circle of points. Component 2 is going to be centered at 4, 4, so in the upper right corner, and its variance is 1 and 1, but it also has covariance of 0.9. So it's going to look kind of like an ellipse pointing from the lower left to the upper right. Okay. Component 3 is centered at -4, -4. It has variance matrix 2, -1, -1, 2. So there's negative covariance. And here, let me just kind of show you the plot. This is going to be kind of the plot of the points. We have, you can kind of see there's a component centered at 0, 0, and there's this big cloud of points in the circle here. You have a component centered at 4, 4, and it's kind of this, but it's high covariance, and so that's kind of this angled point. And then we also have a cluster centered at -4, -4, and there's negative covariance, and that's going to be kind of this concentrated patch over here. Okay. As far as the I guess the PDF of our mixture model, the PDF of our mixture model, I don't know what to do. Well, whatever, okay. We have to, it's going to be the sum of our component of alpha, and then basically this is the PDF of each multivariate normal distribution, okay? And so we're going to say the distribution, okay, of x given our parameters, okay? And so theta, this big bold theta, collects all of the parameters together, okay? All of the different individual theta values. The individual theta, oh dear. The individual thetas are going to be the sigma and the mu's. I don't even know how to just turn it off, is the problem. Yeah. Oh, maybe that worked? Okay, all right. Thetas is going to collect all the parameters here. Okay, so we have the mixture proportions alpha, okay, and that's this vector right here. They add up to 1, and then this p here is just the individual PDF. So this would be the multivariate PDF, and then the z here is basically which cluster does it belong to. Okay, it belongs to either cluster or component 1, component 2, or component 3. Okay, and then so to generate this in R, I have my mixture proportion vector alpha, and then I have the means 0, 0, 4, 4, and negative 4, negative 4 to correspond with that. I have my sigma matrices there. I gather them together into a list, and then to generate this, I use random multivariate norm, and I just say, hey, sample a value, 1, 2, or 3, to decide are we drawing from component 1, 2, or 3. And then when you select that, select the appropriate mean and sigma values, and then generate one random point there using RMV norm. And this is our resulting thing. Now I can label or color the points based on the components that they were generated from, okay? And that's because I generated the data, so I know these data points came from, cluster 2, and these came from cluster 1. So cluster 1 is represented with black, cluster 2 is represented with red, and cluster 3 is represented with green. And I can say, yeah, I know, these points right here came from cluster 3 and stuff like that. But in reality, when we get our data, it looks like this, because the clusters that they came from, or which component they came from, is unknown to us, okay? So it comes in like this, and what we're trying to do is we're trying to take in this basically unlabeled data and figure out, okay, there's 3 clusters here. All right, so that part we have to kind of decide. And we're going to look for 3 clusters, and for these 3 clusters, I've got to find the mean and the variance of each of these things, okay? And, as we do this, if you look at one of these points, right, there's this question of, if I have a point right here, which cluster should I assign it to? Okay, should I assign it to basically the red cluster, okay, cluster 2, which is centered up here, or cluster 1 in black, centered over here, right? Like if I have a point right there, because it's kind of on the border, on the boundary here. And our solution here is, unlike k-means clustering, where we just say, hey, assign it to the nearest centroid, we are going to use a probabilistic assignment. And we're going to say this point right here that's kind of on the border, we might say it is like 51% cluster 2 and 49% cluster 1, or something like that, or maybe 60% this or 40%, and we can kind of go through that for all of our points, and we can say this point really probably is going to be cluster 2, and maybe we'll say like 99% cluster 2, 1% cluster 1, 0%, pretty close to 0 for cluster 3 or something like that. So that's what we're going to do. Rather than strictly assigning a point to one cluster, we will use a Bayes classifier to get a probabilistic assignment. And when we do that, we call that a membership weight. Okay, so each point is now going to have a vector of probabilities that sum to 1 of membership weights. Point number 1 is this probability cluster 1, this probability cluster 2, this probability cluster 3. Okay, and then once you have those membership weights, we can use those weighted values, okay, to calculate the parameters of each cluster distribution. So we'll use like a weighted mean, and we'll also get a weighted variance covariance matrix using the membership weights of the points, all right? And that will maximize the likelihood of the values that are, quote, assigned to each cluster. And we're going to iterate back and forth between calculating the membership weights or estimating these missing values, and then recalculating the parameters of the cluster distributions, okay, the mean and the variance. And so this EM algorithm that we're going to look at is a little bit, you can think of it almost as like a blend between k-means clustering and the Bayes classifier. So in k-means clustering, you had this iterative back and forth. Reassign your points to clusters. Once you redo that, you recalculate your cluster centroids. Reassign points, cluster centroids. Reassign points, recalculate your cluster centroids. Here we're doing something very similar, except rather than just when we reassign the points, we're not strictly saying you're cluster 1 and you're cluster 2 and you're cluster 3. We're saying you are 80% cluster 1 and 20% cluster 2. And you are, 70% cluster 2 and 25% cluster 1 and 5% cluster 3 and things like that. So we're doing this kind of a Bayes classifier when we're, quote, assigning the points to each cluster. And then once you do that, we recalculate kind of our centroids. We recalculate the means by using a weighted mean, and we'll recalculate the variances using a weighted variance. And so, so how do we do that? How do we calculate our membership weights? Well, that is done using the Bayes classifier. And so the Bayes classifier is we're going to do the likelihood times the prior divided by the marginal. So the likelihood is going to be basically what is the probability of getting this particular value. If we know that it came from cluster 1, what's the probability of it getting this particular value if we know it came from cluster 2? And what's the probability of getting this value if it came from cluster 3? And so you need to have kind of initial starting mean and variances for clusters 1, 2, and 3. Okay. The prior is going to be whatever alpha, your vector alpha k, which is how many values are assigned to cluster 1 and assigned to cluster 2 and assigned to cluster 3. And then the marginal is basically the sum of the numerator across all possible classes. Each of these things are a little bit trickier. So when we're talking about the alpha, this is like the prior probability, and this is going to be based on the previous iteration. And it's the prior probability that a point belongs to cluster K. And so we usually, we'll say like if there's 100 points and 60 of them were assigned to cluster 1, our prior probability will be 60% cluster 1. But it's a little bit tricky because the number of points that are assigned isn't actually an integer, okay? This number of points that are assigned to cluster K, this n sub k, is not an actual count of points, but it's going to be the sum of the weights, okay? So when you add up all of the weight vectors, each weight vector adds up to 1, and if you sum them all up, you'll have the number of points total, n, okay? But if you take what is the sum of the first value in each weight vector, that's going to be like this, quote, sum of points that belong to cluster 1. And it's not necessarily an integer. So we're going to basically add up all of the weights for cluster 1, and that will be how many points belong to cluster 1. All of these n sub k's will add up to n, but each of these n sub k's are not necessarily an integer. So that's going to be our membership weights. It's a a weighted like count, okay? And then as far as the likelihood here, that's just going to be the multivariate normal PDF. And we're going to say, hey, what is the probability of getting X if you have this mean and this sigma variance matrix, okay? And this is the PDF for the multivariate normal. Thankfully, we can just use R as give me the density of the multivariate norm. We just say DMV norm, and then we'll plug in our new value and our current estimates of the mean and standard deviation, or a sigma matrix. Okay, so that's how we're going to estimate our membership weights. We need our likelihood and our prior, and then we have to kind of sum them up to get our marginal, but we can do that. I'm going over this quickly because I'm assuming we feel okay with our Bayes classifier, like we did it in the homework. So it's pretty much that. We're using a Bayes classifier to assign these things, and then once you have your membership weights assigned, now we have to update our mean and our variance estimates of each cluster. Okay. Oh, before I forget, your first view quiz answer for today is A. A as in apple. Okay. We recalculate okay. So yes. So we will basically just get a weighted mean. Okay. And I think we're okay with doing weighted means. You give some of these values have higher weights, some have lower weights, and you multiply that by X. You sum them up, and then you divide by our n sub k, which is, quote, the number of points assigned to cluster K, but again, not necessarily an integer, okay? And so that's just going to, the W's that are close to 1 will contribute more, and then the W's that are close to 0, those points will contribute less towards the weighted mean. Okay, same idea for calculating our variances. So this is just the definition of the variance, x minus mu transpose, and this will give us basically a 2 by 2 matrix. But then we weight this by our W, and then we add them up and divide by our n sub k. Okay, so normally you would do this times this and just add them up and divide by n, or divide by n minus 1 to fix the bias. But here we are going to multiply by W and divide by n sub k, however many points are in that cluster. And that's that, okay? And so here, this is how the data come in. They're unlabeled. And so when we do this, we just have to kind of start off with some arbitrary values for the mean and the variance and things like that. So I'm going to just arbitrarily start with 3 centers, okay? 0, 0, 9, 9, negative 9, negative 9. And then my sigma matrices will be just identity matrices, okay? And so these circles, these concentric circles, kind of represent the, what do you call it? Like contour lines of density, okay? So this will be like, I forget what values I use, but like the 60th percentile and 70th, 80th, 90th, 95th percentile, right? And so so right now, these are terrible estimates, okay? And we use the Bayes classifier to assign these points to each of these clusters. And I've colored them based on which cluster has the highest probability, okay? But these graphs are a tiny bit deceiving because it looks like this point right here is assigned to cluster 1 in black, and this point right here is assigned to cluster 3 in green, okay? But in reality, along this border, the points that are colored in black here are like 51% cluster 1 and 49% cluster 3 in green, okay? And then the points that are green over here are like 51% cluster 3 in green and 49% cluster 1 in black. It's just that when you color a point, you have to pick a color, and you can only represent it either with black or green here. But remember, these are not strict assignments. These are probabilistic. So all of these points over here have, you know, some probability of being in cluster 1, and all of these points over here also have some probability of being in cluster 3, and technically some probability of being in cluster 2, even if that number is very, very, very close to 0, okay? So it's probably like 51% black, 49% green, and, you know, 10 to the minus 8 red or something like that, okay? And so that's what I have written on this slide, okay? And then so after one iteration, okay, this is kind of our current assignments, and I update and I say, okay, based on all of the kind of weighted values that are assigned to cluster 1, what is the mean of cluster 1? So this that's going to be this point right here in the center. That's the weighted mean. But then when we ask for its estimate of the variance, you can see the estimate of the variance got much, much bigger because it included all of these points. Okay. Meanwhile, if we look at here, these were kind of the points that were, quote, assigned to the green cluster. And so it took a weighted mean of all of the points that were assigned to the green cluster, and the weighted mean is right here. And then we said, okay, calculate the variance. And the variance matrix looks kind of like this. We do the same thing with red, and this is the variance matrix. And so now we update all of the points and all of their assignments, and we've colored them. So some are black and some are green and some are red. We've updated their assignments. This is what it looks like. And then we'll do another iteration. And then so at the next iteration, we've updated this. And so, you know, previous, look at this, we can see, okay, our kind of our variance covariance matrix for the green cluster is a lot tighter, still kind of centered here, and something similar has happened for red, and this is kind of our variance covariance matrix for all of the points assigned to cluster 1 in black. So we have, and so we're kind of keep updating, and as we do this, we eventually, so let me just kind of, so we started off here, and then just kind of quickly, this is, I think, we end up something like this, all right? And so after some iterating back and forth of updating our assignments and updating the corresponding parameter estimates, this is what we end up getting, okay? And so after letting it run, these are our final cluster assignments, all right? And this is what we have. So this is, again, these points are probabilistically assigned. So the ones that are right on the border are like 51% red cluster 2 and 49% black cluster 1 and things like that. But overall, probabilistically, if we had to just kind of pick one assignment, we'd say these ones get assigned to this cluster, these get assigned to this cluster, everything else gets assigned to the center cluster, okay? We can compare that to the original assignments, and again, the label switching issue of like which one is red and which one is green, that's in play here, okay? But that's okay. They all got clustered together. And you can see these points right here are actually a mix of the cluster centered at -4, -4, and the cluster centered at 0, 0, right? So we can see there is kind of a mix. But then when we did our final cluster assignments, these all got probabilistically assigned to this cluster over here, okay? But in reality, it's going to be a mix, and these points are probably like 95% one cluster, 5% the other cluster. Okay. And so this is what we have. We can compare the true groups because we generated our data ourselves, and so we know what it looks like. And that's what we have. Okay. We could try different starting locations. And so if I started off with this, like I kind of have like bad starting weights and starting locations, and we can just kind of see how this gets updated. So these are different clusters, and after one iteration, this is where we end up. After another iteration, we go there, and we keep going, and also it still manages to converge. Okay, so that is that's encouraging. I want to show a couple examples from Wikipedia. All right, so this is, I guess, a similar diagram. So this is like a real data set. I think this is from, what is it? Old Faithful. So it's like a geyser in Yellowstone National Park, and you can they measured how long the geyser erupts and how long did they have to wait between one eruption and another eruption. And it appears that it's kind of that there's some patterns, and there's like two clusters here that again, you know, they start off with some initial assignments, and then just iteratively they get some kind of convergence here. There's a couple things that the reason why we would want to do this over k-means clustering, and let me see if I can do this and this is in the homework as well. So let's say you have data that look kind of like this. This is like a Mickey Mouse distribution here, okay? So we have a big cluster here, and a cluster over here, and a cluster over here. When you do k-means clustering, it uses Euclidean distance, okay? And it's only able to take into account distance and nothing about variance. And so these points up here, okay, like when we look at this distribution, we can say, oh yeah, you know what, it should belong to this center cluster right here. But because the k-means clustering algorithm is going to like identify a centroid right here, it's going to say, you know, between this centroid right here, this red plus here, and this green circle over here, it's going to put points right here. Are closer to this centroid than they are to this centroid, and therefore it gets assigned to this cluster over here. Similarly, these points that are up here get assigned to this cluster. So it's not able to take into account just kind of like the internal variance, and it's using Euclidean distance. Whereas the EM algorithm, as far as the clusters go, it is able to say, you know what, this cluster of points has a very small variance, okay? And therefore, these points that are out here, even though, like, as far as Euclidean distance go, even though they are closer to the centroid of this cluster up here, because this cluster has such small variance, it is less likely to be assigned to this cluster and more likely to be assigned to the cluster in the center. The cluster in the center has a huge amount of variance, so it's able to kind of, you know, get these points that are way out here. Okay, whereas over here, with k-means clustering, you know, this point that's way out here, it just assigns it to the nearest centroid, okay, which probably doesn't quite make sense. You know, if you say, like, if you take into account the amount of variance you have, you're going to get, you know, a point that's way out here, okay? So if the EM algorithm is able to take into account the sheer amount of variance that exists, and include that with its assignments there, okay? So I have put this in your homework assignment where you're going to have to kind of do some of the basically create these plots yourself. And the guiding principles are really on these slides right here, of calculating your weighted your assignment weights by using the Bayes classifier, and then once you have that, you calculate your weighted mean and weighted variance matrices there. Okay, I guess that's all I have for today's lecture on the EM algorithm. And so we'll wrap things up a little bit early. Answers, last two view quiz answers are C and E. C as in cat, E as in elephant will be our last two view quiz answers. Okay, so we'll finish here, and we'll see you guys later.